All right, in this last section, we'll revisit the linear regression model. So prior to this section, we were just more or less analyzing the scatter plot, explaining the association that was observed, and as long as the association was linear, we can estimate, right? We can more or less predict the response variable given the categorical. The predictor variable. Thinking of ANOVA. Okay, but so in these cases here, we want to revisit it, but now we want to make some further assumptions about our model if we want to use it to make inference. Okay, so to make decisions. All right, so we need to make a few more assumptions about the phenomenon in order for us to do that. Okay, so here, as far as the conceptually the model, so really how the data are generated, how those red dots you see down here, how are they generated? Well, there's a two-step procedure. Okay, one is for a given value of the predictor variable, a straight line determines what value of the response variable should be. So in here I put should be because it's really more or less like the average or typical value. Okay, so it means like, oh well, if you had a bunch of different outcomes for a given predictor value, what our line does, it gives it the average. Okay, not the exact red dot. Okay, so that's kind of what the blue line is, right? Our fitted regression line tells you for a given predictor variable, this is what the response should be, right? For a given caret weight, this is how much the diamond should cost, right? So, but really, if we want to get to from the blue line to the red dots, well, we need some randomness there, right? So we have some random noises added to that blue line in the and what that results in is our observed value, okay, of the response variable. So usually these red dots are a little bit above or below. Okay, so what we say is that, well, this two-step procedure, one is deterministic, meaning there's no probability, right? That line, that blue line, is where it's at, okay, where the typical value should be. But if we want to find the actual observation, well, we need to incorporate the random component, okay, the noise. Right, so meaning it's here with some random noise, here with some random noise, here with some random noise. So it's just, there's two pieces to it, right? So what we were doing before in the previous chapter earlier in the semester, we were just working on the deterministic, that's it. And we were just using it to estimate. Okay, we're saying, look, we observe a linear association, therefore our estimator should work out well here. Right, so we can estimate and fit the data as much as we want. Okay, but the reason we have the random component now is that we want to do hypothesis testing and confidence intervals, right? And for there, you need some kind of random component to it, right? So our randomness comes from the error around our blue fitted line. Okay, so if we just kind of zoom in on the plot, right? Right, so we're just saying the blue regression line is the deterministic part, right? Given 20, I know exactly where the fitted line is going to be. Given 30, I know exactly where the fitted line is going to be. Okay, and then what we have here is the random error. So if I actually want to get to this red dot here, well, first there's my deterministic part, and then I randomly go up or down. So I go down, boom, and there's the dot. Right, so that's the random component. Right, so typically we call it a random error because if you were to measure the distance from this blue line to the red dot, that would be the error. Right, if you measure the distance from this red dot to this blue line, that would also be an error. Right, so if you see my errors, if I'm doing blue line minus red, okay, the y value here minus the y value here, let's say it's 5. Okay, and let's say this is 1, 1, 1, 5, 1. And then let's look at the dots above the line, because I'm doing blue minus the red, so we're going to get negative values. Negative 1, negative 1, negative 1, negative 5, negative 1, negative 2, negative 1. So if you look at the errors, right, between the heights of the red dot and the blue line, they're all more or less centered around 0, right? They're all centered around 0 because all the red dots below here, their errors are positive, and all the red dots up here, their errors are negative. Okay, so what it's telling you is that, you know, when we fit our model, it should be a good fit, meaning it should slice right through the data, right in half, right? So what it means, if we're looking at the errors, right, half of them should be above the blue line, and more or less the other half should be below the blue line. So these errors should be centered around 0, right? So that's what we call this error here. We call it a residual. Okay, and this residual is the difference between the actual observed y value and the predicted y value. Okay, so this is like a measure of the random component. Okay, it is the actual value minus the predicted. Okay, so by examining the collection of residuals, we can understand how real data differ from our straight line predictions. Okay, so this is our straight line predictions, and this is the real world, right? So my residual is the height of this minus the height of this. Okay, the height of this minus the height of this, the height of this minus the height of this, or the y values. Height of this minus height of this. Okay. So things that we need to assume about these. Okay, so now we have conditions for linear model. Okay, we've seen number 1 before, right? Obviously, we have to have a linear trend in order for any of this to make any sense. Okay, so we have to observe a linear association. Check. Now 2 and 3 are new. Okay, 2 and 3 are new. Okay, so 2 now normality. So it's saying the errors or the residuals follow a normal distribution with mean 0 and standard deviation. Who knows what it is, but we'll call it sigma. Right, so remember those errors that we're talking about, right? They should be centered around 0. We're going to have positive and negative differences. We're going to have observations that are kind of above and below the line, right? So they should be centered around 0, right? And with some standard deviation sigma, right? And what this is saying is that the constants, we have to have a constant standard deviation. So it means the standard deviation sigma is the same for all values of the predictor variable. So what that means here is, as you can see here, if we're just looking at this graph here, right, I have actual values above, below, above, below, above, below, above, below, right? So we can kind of say that my errors, they're going to be centered around 0. Okay, now what does constant variance mean? Well, it means that, well, as far as above, below, right, no matter what predictor value I'm at, whether it's 10, or 20, or 30, or 40, if I look above, right, the variation of errors around the blue line is roughly the same. And we see that here, right? So here it's roughly, you know, roughly the same, right? We don't see any trend here, or like we don't see a bunch of values up here and down here. So so that looks good. So we're just saying that what the constant variance is saying is that you know, these residuals, right, if it's, you know, roughly plus or minus 5, right, they're going to be plus or minus 5 distance no matter where you're at. Okay, so it's kind of saying, well, if we have carat weight and predicted diamond price, right, the spread of diamond prices around the blue line, they're going to be about the same. Okay. So one thing that we can do here is, instead of visualizing this graph, is what we do is we'll actually measure the distance and record the number. Measure the distance, record the number. And what we'll do is we'll plot the residuals, which we'll put here on the y-axis, over these here. Okay, and if we do that, then we get what we call the residuals versus predictor variable plot, okay, which is carats. All right, so here I'm going back and revisiting the data we dealt with in an exam, where we're looking at diamond size and price. And so if you remember this data here, it looked a little bit like this. Okay. So we had diamond price in carat, right? So as you can see, as carats increase, the price of the diamond is increasing. And if you were just to look at it here, I mean, all of these errors, they seem to be, I mean, they're all above and below, scattered above and below. And as far as the distance above and below, right, they're all more or less within the same range. Okay, so nothing too crazy there. Okay, so and then, so remember how I did this? If so you go to simple linear regression, plug in your x variable, plug in your y variable, the exact same stuff that we did when we previously covered this chapter, right? But then down here, I'm just asking for more graphs. Okay, I'm asking for fitted line plot, histogram of residuals, QQ plot, residuals versus x values. Right, so I'm just asking it to give me those. Okay, so when I compute it, that's what we get there. Okay. All right, so going back to this example here. So what we're looking for this plot. Okay, so first thing is I include this line of 0 here. So you always got to keep track of where 0's at and include a horizontal line. Okay, StatCrunch by default, it doesn't add this line, and I don't know why, but it should. Because what this does, this is kind of a reference. What we want to do is check, are the residuals centered around 0? Okay, and that's what we see, right? We see, you know, some positive residuals, positive, negative, right? And we see them all centered around 0, right? So we can argue that that these are centered around 0. Okay, that the residuals are centered, that they have a mean of 0. Okay. And so really, what does this value mean? So this is like a residual of 50, right? So it just means that for this observed price of diamond, it was $50 more than the predicted price of diamond. Okay, that's what it means here. If you get something that's negative here, negative 50, it means that the observed price of diamond was $50 less than the expected price of diamond using the regression line. Okay, so that's what all of these mean here. All right, so you can see here, they're all kind of more or less scattered and centered around 0. Okay, now as far as constant standard deviation, well, what we're looking for here is no pattern. Okay, as long as there's no pattern, okay, that is indication that you have constant standard deviation, that these errors are just scattered all around between pretty much negative 50 and 50, no matter what the carat size. Okay, so no matter what the carat size, they're more or less all between 50 and negative 50. Okay, so by using this graph, it's very useful because right away you could check two things. Are your residuals centered around 0, meaning is the mean equal to 0? And 2, do we have constant standard deviation, meaning, okay, they're centered around 0, now is there a pattern? And there's no pattern here. All right, so no pattern indicates that we have constant standard deviation. Now, the reason we need this here is because, you know, we're going to be building confidence intervals and hypothesis tests, but for specific carat amounts. Okay, for specific carat amounts, we're going to build an interval for 0.2 carats, and then maybe build another interval for 0.25 carats and another. So really, in order to be able to move around anywhere here on the x-axis and create a confidence interval or a hypothesis test, we kind of need to have that this normal distribution in the errors and constant standard deviation. So that just kind of backs up the theory, okay, but these are things that we need and we have to check. Okay, we have to check. Now, as far as normality goes, so I kind of showed that the mean is 0 and we have constant standard deviation, but what about normality? So actually you can look at a histogram of the residuals. All right, so this is just a histogram of residuals, and you see they're centered around 0, and we kind of have this unimodal symmetric looking histogram. And actually this curve here is like how they fit of the normal distribution over. So we see it's a pretty good fit, right? And just as a reminder, how I did this was I selected, you know, my predictor, my response, and then of course down in here I'm selecting, so I hold this button down, right? I'm selecting these here. Alright, so hold it down. Okay, so it depends on what computer you have. If you have a Mac, you hold it down Command. If you have PC, hold it down. I don't know what it is, control or something. Okay, but that's how I'm getting all these graphs here. Okay, because when I compute, then all I do is, okay, of course I have my table here, but I just hit these arrows. Okay, there's my line, there's my residuals, there's my so see here the residuals versus carrots, they don't add this line, so you need to envision a horizontal line here at 0. Okay, you have to envision this line at 0. Okay, because you could look at something like this, but say it went like 0, 50, 100. Well, that's telling you residuals, they're all positive, right? They're all positive. So we need to really make sure that they're centered around 0. So whenever you see these residuals, just draw a horizontal line here at 0 and say, okay, or half above and half below. Okay, you have to check that. Okay, so here, I mean, yeah, so we get a normality sense. So we verified our assumptions, okay? Just another plot that they use as well to check for normality in the residuals. And I'll just kind of give you the gist of what it does, but it's really the most popular, right? I mean, we look at these histograms, but this is a more popular graph to use, and it's called a QQ plot. And what it does, it compares quantiles with quantiles, or percentiles with percentiles. So what it does with the residuals is that it'll order them from smallest to largest, and then it'll find the percentiles. They'll find the first quartile, you know, the second quartile, the median. It'll find the 75th quartile, right? And then what it does is it standardizes them. Okay, meaning that it'll find the average residual and divide it by the standard deviation of residuals, right? And so what you get are z-scores. Okay, are z-scores. And so what they do now is they compare the z-scores that we found from the residuals to the theoretical standard normal percentiles. Okay, and pretty much what we're looking for is a one-to-one correspondence. Okay, one-to-one correspondence. So pretty much what we're doing is these residuals, we're standardizing them, and we're just saying, well, how well does a standard normal distribution fit the standardized residuals? Right, and so here we more or less see it's like a almost perfect one-to-one fit. Okay, of course some a little high, some a little low, but other than that, that's what we use this for. If it's not one-to-one, then it's what these can tell you is maybe your distribution is skewed to the left or skewed to the right, or maybe it has a lot of variation, and so that's what these are used for. Okay, but the QQ plot is the most popular. Okay, but that's all we have. On next time we meet, we'll cover the rest of chapter 14, and that will conclude new material. But we more or less revisited this linear regression model, and really we're saying, okay, we know how to build this fitted line. Okay, we know how to build this fitness line, and we know how to estimate using this fitted line. But now we want to get into more formal statistical inference methods, okay, meaning hypothesis testing, confidence intervals. So in order to do that, we need a few more things. Okay, we've already been checking whether or not it's linear, but now we get into, okay, these errors between our model and the actual data, they should be centered around 0 with a constant standard deviation, right? And really the best plot for checking that is this one right here. Okay.